Welcome to episode 6 of our series on business cycles. With the triple wave model complete, today we begin the second, historical half of the book, the methodological challenge of verifying this theory against empirical data.
It's an absolutely essential pivot. And for you, the listener, it's really where the philosophical rubber hits the road.
Right.
For the last 5 deep dives, we've built this rigorous theoretical machine.
Right.
We called it the analytical apparatus of economic evolution.
Laid it all out.
We did. We established the mechanism of innovation, which was E1. Then we traced it through credit expansion, structural adjustment, E2, E3, E4, all the way to the formation of new equilibrium neighborhoods in E5.
So we had our beautiful clockwork, a perfect model showing how a purely theoretical capitalist economy moves. But that was, well, it was all pure theory.
The perfect model, exactly. Now we have to bridge this enormous divide.
A huge one.
From that clean theory to the messy, contradictory, and deeply incomplete historical record. So we're moving from the realm of pure mechanics, what the sources call E1 through E5.
To the historical verification chapters, E6 through E10.
That's right. And the central question just completely shifts. It's no longer, how does the cycle operate in theory?
Now it is, how do we actually see that theory?
How do we see that theoretical process? The birth, life, and death of these 3 superimposed waves of innovation. How do we see that in the real-world historical record?
In the actual graphs of prices and production and employment over the last 2 centuries.
And this is, I would argue, the most difficult step in the entire framework.
And this is exactly where this methodological conflict comes in. We have to define the rules of evidence for economic evolution.
We do.
Because we can't just reach for the standard statistical toolbox.
Absolutely not. That's the first and most important rule, the standard tools. The ones that economists and econometricians rely on.
Regression analysis, that kind of thing.
Exactly that. Regression, standard error measurements, frequency distributions, they're all deeply rooted in a foundational assumption, a really strong one.
Which is that the world is stable.
The assumption of a stable environment, or what statisticians will often call a stable universe. They assume the underlying rules of the game are fixed.
Right, like you're trying to predict countless coin flips, and you just assume the coin itself never changes. It's always 50-50.
Precisely. But the economic world we're studying here, this capitalist engine driven by innovation, it's fundamentally defined by the opposite of that. It's defined by irreversible, revolutionary change.
It's constantly breaking its own rules.
It's constantly shattering its own equilibrium and replacing the old system with a new one. So if the underlying structure is always shifting, constantly evolving, well, the statistical tools designed for static systems, they just fail.
Or worse.
Or worse. They produce spurious results that don't confirm anything except their own flawed assumptions. So we have to start somewhere else. We have to start with history.
Okay, so let's start there. Let's talk about what makes that historical record so messy and, frankly, so hard to quantify. And it's the constant, undeniable interference of what the sources call outside factors. If you look at any stretch of economic time, the reality is that the purely economic cycle is just constantly being distorted.
All the time. I mean, take the period of the French Wars. You're looking at 1792 through the early 1800s.
Yeah.
You had the suspension of specie payments. You had the trade war with America. You had these monumental geopolitical shifts happening. Or, a clear example maybe. Consider the British economy around 1846.
The repeal of the Corn Laws.
Exactly. The repeal of the Corn Laws. That was a massive, sudden policy reversal on grain tariffs. And it didn't just cause some small blip on a chart.
No, it fundamentally changed the entire structure.
It profoundly reshaped the cost structure and the dynamics of British trade for decades to come.
That's a great example. These aren't small, independent, random variables that just average out nicely in some probability scheme.
Not at all.
These are massive, unique, game-changing shocks. Policy shifts, wars, revolutions, natural catastrophes.
And they are ubiquitous. They're everywhere. We see it later on, too. There's a fascinating example from the beginning of the 1931 world crisis.
What happened there?
Well, there was a clear, discernible upward movement in economic indicators early in that year. It really suggested a recovery from the previous downturn was underway.
So things were looking up.
But that recovery was completely broken down, completely reversed by the intense political flutter caused by the reopening of discussions about a potential union of Austria and Germany.
Wow, so a political event just completely derailed the economy.
Completely. The incident movements of short balances and the capital flight that followed. They profoundly shaped the entire recessionary path that came after. The point is this. The sheer scale and frequency of these external shocks means that virtually every single economic fluctuation we observe in real data is, to a certain extent, a historic individual.
Meaning you can't just treat the 1929 crisis and the 1873 crisis as if they're statistically identical units drawn from the same stable bucket.
You absolutely cannot. And because we have this continuous stream of external factors, which are, often not small, not independent, and certainly not numerous in the probability sense, understanding any specific cycle requires what the source material calls a minute historical analysis.
You have to get into the weeds of that specific time.
You have to look at the innumerable factors actually at work in that specific time and place. And this is why, focused, detailed historical study, the actual conquest of past fact, is sometimes deemed more important than just collecting more and more data today.
Because more data just increases our knowledge by, infinitesimal steps.
Exactly. We need context first.
So historical context is paramount. But even within the economic process itself, if we could somehow set aside those external shocks for a moment, we need a clean framework for analysis.
We do.
And that means we have to strictly distinguish between the two fundamental drivers of internal economic change, growth and innovation.
This distinction is absolutely crucial for understanding why we have to reject the standard statistical idea of a trend. So let's define them. Growth refers to continuous, smoothly absorbed changes.
Okay.
Think of it as the constant, steady background hum of economic activity. Something that, if it happened in isolation, the system could handle without any noticeable disturbance.
Like population growth.
That's the perfect example. The gradual yearly increase in the labor supply, maybe a few percent per year, or the slow accumulation of capital through simple saving. If economic change was only made up of these smooth growth factors,
Then the math would work.
then the concept of statistical trend determination using mechanical methods like least squares to find the smooth baseline would make perfect economic sense. The system would remain fundamentally stable, just a little bit larger each year.
But that theoretical stability is just completely shattered by innovation. That's the core driver of the cycles we're actually interested in.
Yes. Innovation is the introduction of irreversible change in the production function or the way of doing things. It's fundamental discontinuous.
It's a leap.
It is a leap. The change is not smoothly absorbed. It requires a revolutionary jump, followed by a period of destructive adjustment before a new equilibrium can be reached.
And this is where that classic analogy comes in, right? You can't get there by just adding more of the same.
You cannot. You can add as many horse-drawn male coaches as you want. That's just growth. You're just getting better at the existing technology. But you will never, ever, by merely adding more coaches, invent a railroad.
It's a different category of thing.
A different category entirely. The railroad is a qualitative revolutionary shift that requires a completely different analytical approach. It represents a break in the theoretical normal, not just a small increment above it.
And this brings us to a really critical methodological declaration right up front, and this comes from our supplementary material on the analysis of economic change. We are not using statistics to discover the cycle.
Absolutely. This is so important. Statistical measurement is primarily a tool for illustration and for quantification after the fact. We're not setting out to prove the existence of the cycle mathematically, as if we were discovering a new planet through orbital calculations.
So what's the goal of the history, then?
The primary fact to be proven by historical research is the industrial change or evolution that we established in the theory. The fact that innovation clusters and drives cycles in a revolutionary way.
So the math just helps us see it more clearly.
The mathematics merely helps us visualize or refine the contours of that historical reality. It's not the proof itself. History and theory lead, statistics follow.
Now that we understand that history is chaotic and change is revolutionary, we can really appreciate why the standard statistical toolbox just falls apart.
Right.
So we have to look really closely at how the sources define the variables involved. To frame this whole statistical problem, we need to understand the relationship between three distinct categories of variables:
Theoretical, stochastic, and historical.
Let's start with the first two. They sort of define the boundaries of where pure statistics can even be applied. What's a theoretical variable?
A theoretical variable exists only in an assumed closed system where all the functional relationships are perfectly known. So if we imagine that ideal state of Walrasian general equilibrium.
The perfect circular flow where everything balances.
Exactly. In that world, The quantity demanded for a good, or its price, is a theoretical variable. Its value is defined entirely by the established laws of the system.
So if we know the demand curve and we know the supply curve, we know the equilibrium price. Time, in that context, is sort of irrelevant.
Precisely. Time is merely a coordinate. It has no necessary relation to any particular historical period. The law is established and it transcends the actual observations. It's like the immutable rulebook of a perfectly closed game.
Okay, so that's the pure theory world. Then we step slightly closer to reality with the stochastic variable, or aleatory, as it's sometimes called. This is what most applied statistics is actually dealing with.
And the stochastic variable is defined precisely by the absence of a known theoretical law that explains its variation. We don't understand why measurement errors vary in the same way we understand gravity.
They're just facts.
They're mere experimental facts. We analyze them using frequency distributions, and we assume they behave like pulls from an urn that contains an invariant proportion of different colored balls.
So the variation is random, but the system that's creating the variation is stable.
That is the strong limiting condition that allows the mathematics of probability to work. The values, real and possible, must constitute a stable universe. Think about it. If you're measuring the height of soldiers in a specific regiment in 1890, the mean height, the statistical norm, should be stable.
All right.
The variation around that mean is just stochastic error. But if that underlying stable universe, the population of that specific regiment, starts to shift, the probability reasoning just collapses. The tools assume a fixed target.
So if the theoretical variable has a fixed law, and the stochastic variable has no fixed law but a stable statistical universe, where does the variable representing the actual evolving capitalist economy fit in?
Well, it occupies the most challenging ground of all, the historical variable.
Okay.
This variable is a hybrid of the two, but it possesses what is a fatal flaw for standard statistics. In the historical variable, its stochastic norm changes precisely because its theoretical norm changes.
The target moves while we're trying to measure the random scatter around it.
That's it exactly.
Okay, let's elaborate on this. This displacement of the theoretical normal. This feels like the core of the methodological break.
It is the core. Consider the price of a critical input, say steel, over time. If the economy is in a circular flow, that price is stable. That's the theoretical normal. Small, temporary fluctuations around that are purely stochastic errors.
Okay, stable world.
Now, innovation hits. A new, vastly cheaper method of producing steel is introduced.
The old equilibrium is instantly obsolete.
The entire system is thrown into disequilibrium. During the cycle of adjustment that follows, the price and quantity of steel move all over the place. But these new values, they are not just stochastic errors around the old price.
They're on a whole new playing field.
They are successively on different demand and supply curves because the cost function, the supply curve, is constantly shifting because of the innovation process.
So the economic law that's governing the variable is literally displacing itself over time.
That's the key insight. The old theoretical normal, the price under the old technology, is destroyed. It's gone. And it isn't replaced by a new, stable normal until the system fights its way back to a new neighborhood of equilibrium.
One that adapts to the new, evolved world.
A world with cheaper steel and whole new industries using it.
So this means that any time series representing a historical variable, say GDP or investment over 50 years, is made up of values that fundamentally belong to entirely different theoretical systems at different points in time. It's like trying to measure the velocity of a comet that's constantly changing its orbit because of its own internal revolutionary thrusts.
And this, you see, is the deep fundamental reason why standard statistical methods that are rooted in probability schemes, which absolutely require a stable universe and fixed theoretical laws, become strictly inapplicable when you're dealing with economic evolution.
You can't use them.
Applying them mechanically, especially trying to mathematically decompose a time series, runs a very serious risk of yielding entirely spurious results. The inherent nature of economic evolution violates the very preconditions of the probability calculus.
And beyond this huge theoretical breakdown, we also face a brutal practical constraint. We just don't have enough material. We don't have enough data to run meaningful, robust statistical tests.
And this quantitative constraint alone just defines the sheer difficulty of the task. Even if we could somehow manage to adjust for the shifting theoretical normal, the amount of material we have covers a dangerously low number of observational units.
And the cycles themselves are the units of observation.
That's right.
So how many juggler cycles, those medium waves running 9 or 10 years, how many of those do we actually have?
Well, for the most favorable time series before the First World War, we only have about 12 to 14 available cycles.
That's not a lot.
That is barely enough data to form any sort of robust statistical generalization, or to reliably apply standard methods that are designed for large samples.
And the situation is far, far more desperate for the long waves, right?
Yeah.
The Kondratieff cycles, which run 54 to 60 years.
It's absolutely terrifyingly desperate, statistically speaking. Up to 1914, we have a little more than 2.25 complete units available.
2.25. So you're telling me we're building a theory about a 60-year pattern based on barely 2 full observations?
I mean, it sounds statistically reckless, doesn't it? Even if the historical narrative is strong.
It does.
And it is statistically insufficient, period. Trying to draw significant statistical conclusions about a 60-year pattern based on 2 or 3 complete observations is just, it's statistically unsound.
So you combine that perilously low number with all the ever-present external and internal irregularities.
The historic individuality of each cycle.
And the rigorous statistical task becomes virtually impossible.
It does. We have to accept that we must rely primarily on detailed history and qualitative economic analysis, and only use statistics as a tool for illustration.
This methodological challenge leads us directly to one of the most fraught concepts in standard business cycle analysis, which is the secular trend. The standard procedure always dictates that you have to filter out the long-term underlying trend, this supposedly smooth growth component, before you can analyze the specific cycles that fluctuate around it.
And this is where the theory of economic evolution makes a really revolutionary break with standard econometrics. We have to fundamentally reject that notion.
The notion that the statistical trend is an independent, smooth line caused by separate, benign influences.
Right. When statisticians define trend, they simply mean monotonically increasing or decreasing mean values over successive subintervals. Historically, economists would then apply mechanical methods, like least squares regression, assuming this trend represented smooth, independent growth from external factors.
But the theory argues that, setting aside the tiny element of smooth population or capital growth, the secular trend is not due to independent influences.
That trend is, in fact, the result of the cyclical process of innovation itself.
Okay, say more about that.
It is the historical embodiment of the net long-term results of successive cyclical fluctuations. Think of it like this. Every time a wave of innovation in Juglar cycle occurs, it introduces revolutionary new methods, new industries, new productivity levels.
Right.
When the economy settles back down to its new neighborhood of equilibrium, it does so at a higher plateau than it was before.
The plateau itself has moved up. It's like climbing a mountain using a series of discrete, exhausting jumps rather than just floating smoothly upward on an escalator.
That's a perfect way to put it. The resulting long-run average increase, that trend you see on a graph, is not due to some separate, smooth engine running in the background. It's the cumulative sum of those discrete, revolutionary, cyclical advances.
This is a really grounding insight because it completely invalidates the standard mechanical detrending methods.
It does.
Applying purely formal methods, like fitting a straight line or a fixed curve using least squares, to these result trends is it's entirely unwarranted. It assumes the effect is the cause.
You're trying to separate the cause from the effect when they are intrinsically linked. If you mechanically remove this statistical trend with a formula, you are actually removing the very phenomenon you're trying to study, which is economic evolution.
You're throwing the baby out with the bathwater.
Completely. You're treating the accumulated impact of revolutionary innovations as mere background noise that has to be filtered out before you can analyze the real cycle. And that is a massive methodological error.
It's like trying to measure human evolution by fitting a trend line to the height of 5 random generations and then saying, okay, we've removed evolution, now let's study what makes people tall or short. You've literally removed the irreversible cumulative changes themselves.
It's a perfect analogy. We cannot separate the path, the trend, from the steps, the cycles. And this is why we have to anchor our analysis not to some arbitrary statistical line, but to a genuine theoretical reference point.
The theoretical normal.
The theoretical normal.
And we know what that theoretical buckline is. It's the circular flow.
Yes, the circular flow represents the ideal, unchanging, repetitive economy without any innovation. That is our theoretical line of zero deviation. All the observed movement, the deviations, must be measured against that
But because of innovation, that line of zero deviation is constantly shifting upward.
in discrete steps.
So the crucial challenge then becomes locating these normal points, or these neighborhoods of equilibrium, in the actual graphs of time series.
Absolutely. And these are not random points. They are the specific points in time where the system has absorbed the previous wave of innovation and has settled, just for a moment, into a new, higher, or different steady state.
They synthesize the net result of the evolution.
They do.
Yeah.
And they are of fundamental importance because they serve as reference points for the irreversible path of economic development. They are the stepping stones across a stream, as the sources describe them.
And if we can identify those points historically, that gives us the true path of growth.
Precisely. A line or a band connecting these discrete normal points forms what we call a tendencia de resultados, a result trend.
Okay.
This specific non-continuous line has true economic significance because it's derived directly from the theoretical structure of the economic process. It is the path of new, evolving equilibriums,
So this approach ensures we aren't just relying on a purely mathematical moving average.
which is just a visual aid.
Yeah.
It has no inherent economic meaning. We have to locate these stepping stones using detailed historical evidence first.
Okay, so once we've established that the underlying path is this result trend, the accumulated stepping stones of innovation, we then turn to the second major statistical hurdle. And that's decomposing the observed fluctuations into their component cycles based on the triple wave hypothesis.
Right. We have to assume, for analytical purposes, that the data we observe is the result of the simultaneous interference of three distinct innovation-driven cycles.
Kitchin.
Roughly 40 months or 3.3 years.
The medium Juglar.
9 to 10 years.
And the long Kondratieff.
54 to 60 years.
Yeah.
The line we actually draw on a graph is the superposition of these three roughly sine-like movements.
And this simultaneous interference creates a massive technical and logical challenge when we try to do any formal decomposition, even if we assume the theory is perfectly correct.
It does. I mean, using purely formal mathematical methods like spectral analysis or Fourier analysis to decompose a time series into these components, it's deeply problematic. Strictly speaking, it's illogical without introducing additional economic meaning first.
Can you simplify Fourier analysis for our listener? What's the basic idea?
Imagine Fourier analysis as a tool that's designed to predict something perfectly periodic and stable, like ocean tides.
Okay.
It assumes a repetitive, stable pattern, and it tries to break down the observed wave into its underlying fixed frequencies. And this works beautifully when you have a stable universe, like the gravitational relationship between the moon, the sun, and the earth.
But innovation means our tide patterns are constantly and irreversibly changing.
Exactly. So we're applying a tool that's designed for stability to a process that is defined by instability.
The wrong tool for the job.
Entirely.
Yeah.
Formal methods rely heavily on probability schemes and stable periodicities. And since our observed material is so highly exposed to external factors, and since the underlying statistical universe is shifting, the theoretical normal is moving, these formal methods are just strictly inapplicable to historical variables.
So you can't rely on the math to find the components.
We cannot rely on these methods to discover and isolate the components. They can only illustrate what the theory has already postulated.
To bring this complexity to life, the sources reference some illustrations that were created under these idealized assumptions. This thought experiment seems really crucial.
It is. It's so important for understanding the challenge. Imagine, just for a moment, that the Kitchin, the Juglar, and the Kondratieff cycles were behaving in the most unrealistically perfect way possible.
Constant periods, equal phases.
Perfect integer relationships between the waves. And we plot three perfect sine curves, one for each cycle, with amplitudes proportional to their duration.
So you've got these three beautiful regular waves. Now you combine them to create a composite curve. That's the curve that represents the actual observable data. What does it look like?
The resulting composite graph looks incredibly irregular.
Really?
Chaotic to the naked eye.
Okay.
And if you look at the rate of change in that composite curve, the first differentials, it looks even more volatile and erratic.
That's fascinating. And I have to say, wonderfully depressing for a statistician.
Lives. It is.
The universe could be running perfectly smoothly beneath the surface according to three distinct laws, and all we see in the resulting data is just a giant squiggly mess.
This thought exercise illustrates a fundamental paradox. Extreme mechanical regularity in the underlying components can produce a composite result that appears highly chaotic and irregular.
So just looking at it isn't enough.
This immediately shows that identification by mere inspection, or by trying some simple mechanical moving average, is entirely insufficient for verification. The human eye cannot easily separate the 40-month Kitchin wave from the 9-year Juglar wave, let alone when constant external shocks are distorting the picture.
And this just emphasizes, again, the necessity of economic theory leading the statistics, that principle of economic meaning.
Correct.
Yeah.
We're not just blindly throwing data at a mathematical formula, because we know from the analytical work that these 3 cycles should be there, and because the theory has specifically tailored the periods to be significantly different, 3 years, 10 years, 50-plus years, we're more comfortable applying specific statistical tools.
But only as rough approximations.
Only as rough approximations that have to be validated by history.
So statistical tools aren't rendered completely useless, but their role is purely supportive.
Purely supportive. While the strict application of probability-based methods is flawed, methods like Fourier analysis or the curve-fitting approach developed by Dr. Georgescu, they sometimes produce results that detailed history allows us to accept as approximations.
So it's history that validates the math.
It is history that validates the mathematics, not the reverse.
And the success of even some very primitive methods seems to reinforce the underlying reality of the structure.
It does. The early work of economists like Kitchin achieved notable success just by counting their short cycles and observing that 2 or 3 of them seem to form the higher-level Juglar cycle.
Just by eyeballing it, essentially.
And this surprising success using such crude methods suggests that the material possesses some underlying strong structure, the strong, irregular, inherent mechanism driven by innovation that exists independently of any statistical sophistication.
The historical reality of the structure is so strong that even crude methods can pick it up.
Exactly. It allows crude methods to work where sophisticated, non-contextual methods might fail entirely.
Okay, we've established a very clear boundary throughout this deep dive. Economic methodology can't just borrow off-the-shelf statistical tools that were designed for physics or biology. The economy is fundamentally different because it evolves irreversibly.
And that core lesson has to be stated definitively. Statistical methods cannot stand on their own. They must be developed from the theory of the models they are applied to. The theory provides the necessary a priori knowledge.
The pre-existing understanding.
Exactly. That understanding is what guides the inevitable guesswork involved in interpreting messy historical data.
And this leads us right back to the non-negotiable guiding philosophy we have to adhere to.
The principle of economic meaning.
What does that mean in practice?
This principle demands that every single statistical procedure, from determining the trend to isolating a specific frequency, must be fully translated into instruments based on empirical knowledge of the phenomena being handled.
So if a statistical technique produces a trend line or a cycle period or a correlation coefficient that can't be explained or validated by historical facts or the economic theory of innovation,
that result must be discarded as spurious.
Regardless of how statistically significant it might appear on paper.
Correct. We can't simply trust a high R-squared value if the result contradicts what we know actually happened historically. The validity flows from the historical context to the statistical representation, not the other way around.
This emphasis on specific knowledge, it leads us to a challenging final conclusion about the current state of economic data.
It does. We often don't have adequate quantitative accountability for many fluctuations.
So we can say things are true qualitatively, but we can't really pin down the exact contribution of any single factor.
And that's the difference between useful economics and what is often deemed useless by the practical person. It's one thing to say that the inertia of wages, the fact that wages don't immediately fall during a downturn, contributes to unemployment.
It's obvious.
It's obvious. It is an entirely different and essential thing to know how much that element contributes.
To quantify the impact.
Yes. Does wage inertia account for 1% or 90% of the observed unemployment figure in a specific time and place, say in Pittsburgh in 1932? Without that detailed quantitative answer, economics remains a science of qualitative generalities.
But the theory could provide an answer.
The general analytical apparatus we've developed could turn out a definite quantitative answer, but only if the necessary factual information, the specific elasticity, the exact rigidity were inserted into it.
So the path forward is clear. It's a shift toward granular, empirical, historical comparison and quantification.
Absolutely. If the cycle is truly driven by industrial change, by innovation clustering, then its mechanism can only be fully established by covering in detail all recorded cases of such change.
We need focused historical research that moves beyond just general impressions and really establishes the mechanics.
We need to see the process of disruption repeated across different centuries and different technologies.
We need to compare, for instance, the development of the English iron industry from the 16th to the end of the 18th century, including the introduction of coke smelting and puddling.
With the rise of the motor car industry in the 20th century, we need to find the striking similarities in the process of disruptive entry, financing, diffusion, and eventual absorption into a new equilibrium.
So the goal, then, is to move beyond mere belief in the theory and establish its validity through detailed, quantified historical evidence.
To confirm that the innovation schema produces, together with its necessary monetary complement, the specific kind of waves inherent to capitalist society.
We've set the methodological framework. Now we are ready to open the history books. So what does this all mean? We've established that verifying the triple wave theory is fundamentally a task of historical analysis, with statistics playing a supporting role guided only by the principle of economic meaning. The history dictates the statistics, not the other way around, because the economy is evolving, not static.
The methodological framework is now set. We understand what kind of evidence we are looking for in the historical record evidence of discrete revolutionary change, not smooth growth. We are looking for those crucial stepping stones of new equilibrium, marking the undeniable, irreversible evolution of the capitalist engine.
Having defined the rules of evidence, in our next episode, episode 7, we will begin the historical verification process by examining the first era of capitalism, 1787-1842, and the Kondratieff cycle of the Industrial Revolution from chapter 6.